Okay, I think you can start. Last week we looked at what mass is as a measure of inertia, which is just the resistance of a body to change its position or to change its velocity when a force is applied. And we saw that mass is measured in kgs, and that previously the kg used to be defined in terms of an object, a cylinder of platinum and iridium, an alloy of platinum and iridium, but since 2019 that is no longer the case, because there has been an effort to change how we define the units of these physical quantities in terms of, not in terms of objects, but in terms of physical constants. Okay, so the definition of the kg has changed, but what has not changed is the amount of inertia. Okay, the inertia is still the same. We also looked at what length is, which is a straight line distance between 2 points on an object, and that length is measured in meters, and that previously length used to be measured, the meter used to be defined in terms of this bar, this X-shaped bar of platinum and iridium. And again, since 2019, the definition of the meter is no longer in terms of this bar. We define the meter as the distance light travels in vacuum during a time interval of 1 divided by 300 million of a second. That is how we define the meter. So that's what we did last week. I think we also talked a bit about time, what time is and what kind of time we are interested in. What we are interested in is the interval or the duration between the start and the finish of an event, or between two separate events. So our kind of the kind of time we're interested in physics is the duration. There is a time you wake up. We're not interested in that kind of time. What time you're supposed to have lunch. We're not interested. But the kind of time we're interested in is, for example, how long was your lunch? So having lunch is an event. So how much time, what was the duration of your lunch? Was it 30 minutes or was it 10 minutes? That's the kind of time we're interested in. Okay? And we saw that the SI base unit for time is the second, and the second is defined as follows. 1 second is defined as a duration of 9,192,631,778 periods of light emitted when the outermost cesium electron transits between two hyperfine levels of ground state cesium 113. So this is a schematic or a diagram of what cesium 113 looks like. So if this outermost electron moves from this energy level, the shell in which it's in, to join these other ones here, for that to happen, this electron needs to give up some light, or needs to give up some of that energy. And when it gives up some of this energy, it shows up as light. That light has got a wavelength and a period, a very, very small wavelength and period, which is emitted. So that period, which is a small duration of time between the two crests of light, which are emitted when this outermost electron changes energy levels. So the light which is emitted is a wave, which means there's got wavelength, and it also has a period. So the period of that light multiplied by this 9.2 billion basically of this light that is what we call, or that's what is defined as 1 second. So this is a very, very small amount of time. This is a very, very small duration. Do we have any questions so far on these three? What mass is, what length is, how we measure the mass, how we measure the length. When you're talking about time, what is it we mean? As I've said, there is a difference when it comes to time between when you have your lunch or when you have your supper. Robson, can you switch off your microphone? So we are not interested in what time you have your supper or your lunch. The kind of time we're interested in is how long was your supper, the duration of your supper, or the duration of your lunch. Was it 5 minutes? Was because that bit is an event. Okay, so we are interested in how long these events are. That's the kind of time we're interested in. Okay.
Sir.
Yes.
Excuse me.
Yes.
You said how should we calculate our mass?
How should we calculate our mass?
Yes.
You don't calculate mass, you measure the mass.
How do we measure?
You use a scale. You use a scale.
Okay.
Yeah, that's all. For you to measure mass, you use a scale. Use an instrument called a scale. Yes. Any other question? I want people to speak. Don't write messages. So if you have a question, please speak out. Switch on your microphone, then speak. Okay. Otherwise, I will not be attending too much to text messages because that will take me away from this teaching thing which I have to do. Okay, so the next thing is temperature. Okay, now temperature in our day-to-day life basically refers to how hot something is or how cold something is on a scale. Okay. However, the definition of the kind of temperature we are interested in physics is different. What we are interested in a physics course, when we talk about temperature, we actually mean something called thermodynamic temperature. This thermodynamic temperature basically measures the following. It is a measure of the average total internal energy of an object. Internal energy of an object refers to all the energy which an object has. So you get each and every atom which makes up this particular object, then you measure how much energy all these atoms have, whether it's vibration, whether they're moving, whatever it is, all their energy. Okay? That's what's referred to as internal energy. For us to measure internal energy, we basically, this internal energy is related to temperature, and the temperature is related to, is what's referred to as the thermodynamic temperature. So later on during the course, we will see how this temperature, this internal energy and temperature are related. But for now, it's sufficient, okay? It is enough to know that what we refer to as temperature in physics is actually a measure of how much energy an object has. So the more energy an object has, the more the temperature. Okay, the less energy, the lower the temperature. Okay, and this thermodynamic temperature is measured in kelvins, so it's different from the temperature which you measure in degree Celsius.
Your microphone is off. Microphone is off. So we can get you. The lesson
Okay, so we move forward. Okay, so what we refer to as temperature is actually a measure of this thing called internal energy. However, internal energy is not easy to measure. Okay, it's very difficult for you to get into a substance, then you start following up each and every atom, measuring how much energy they have. Then at the end of the day, billions of these atoms, you add up all their energy so that you can have internal energy. So there is an indirect way of measuring internal energy, and that is through the temperature. Okay, and the temperature we are interested in, which we use, the temperature which is related to internal energy, is what this thing we are calling thermodynamic temperature is, measured in kelvins. Temperature is also related to something else. It is related to heat. Heat and temperature are not the same thing. Okay? Heat and temperature are not the same thing. If you have a hot object, something you consider to be hot, that means that that particular object has a lot of internal energy. If you have a cold object, then it means that that particular cold object has less internal energy. If you put a hot object next to a cold object so that they touch each other, we know that some of the heat is going to move from the hot object to the cold object. What we consider to be heat to be transferred from the hot object to the cold object. So when this transfer happens, the cold object is going to warm up, and the hot object is going to cool down a bit.
Excuse sir, I can't see the screen.
You can't. Okay, fine. Okay, hope you can see it now. Yeah, so as I was saying, when you put a hot object which has got more internal energy, therefore a higher value of thermodynamic temperature, next to a cold object, the hot object is going to lose some of its energy, and that energy is going to be transferred to the cold object. Are we clear?
Hello?
Yes?
Sorry sir. I'm unable to see the screen.
I've shared the screen. Are other people not seeing the screen?
The screen has been turned on. It's not clear, sir.
What is not clear? I've shared the screen.
We cannot see it. You have to zoom in.
You still can't see the screen.
We can.
Yeah, I've shared the screen. It takes a bit of time.
We can see.
Yeah, it takes a bit of time where I am and for it to reach where you are.
Yeah. The network.
Okay. So, what I was saying is, the hot object has got a lot of internal energy compared to the cold object. So if you put a hot object in contact with the cold object, some of the internal energy from the hot object is going to be transferred to the cold object. This internal energy which is transferred, that is what is referred to as heat.
We can't get you, sir.
Are you able to hear me?
Yes, we can hear you.
So, the internal energy transferred, a portion of the, not all the internal energy, but a portion of the internal energy transferred from the hot objects to the cold objects, that is what we call heat. So basically, heat is internal energy which is transferred between two objects, from the hot object to the cold object, or from the cold object, from the hot object to the cold object, like that. Okay. Then the Kelvin is the unit for thermodynamic temperature. Okay. And how do we define the Kelvin? the definition of the Kelvin is based on what you're seeing here in this class. Okay, so there's ice cubes, there's water, and there's some gas bubbles. So what we have here is what's known as a triple point. A triple point is a condition where a substance exists as a solid, as a liquid, and as a gas. So our water in this case, in form of ice cubes, is existing as a solid. In form of the liquid, the water itself is a liquid. Then in form of gas bubbles, it's existing as a gas. However, this condition, which is the triple point of water, you don't see it quite often because it requires specific conditions to be met. One of them is the temperature. The temperature has to be 273.1615 or 0.01 degrees Celsius, and the pressure has to be 0.61 kilopascals. So you can see the temperature in the units we measure temperature, the ones we're used to, 0.01 degrees Celsius. That's what you're used to. That's a very low temperature. Okay? And in the Kelvin scale, in kelvins, this temperature of this class, for these things to happen, the temperature is 273.1615 kelvins. Then there's pressure also. The pressure of the air in which this glass is. Currently, wherever you are, the air you're breathing in has a pressure of 101 kilopascals. That is what's referred to as atmospheric pressure, 101 kilopascals. So if you pump out a lot of this air, okay, then you remain with very, very little, probably close to a vacuum or something like that. So you're with a very low amount of pressure, then you reach this pressure 0.61 kilopascals or 611 kilopascals. So the pressure has to be very, very low, 0.61 kilopascals. Then the temperature also has to be low, 273.1615 kelvins. At these two conditions, temperature 273 kelvins, pressure 0.61 kilopascals, then you can have this phenomena happen, which is the triple point of water. Okay, so the Kelvin is defined in terms of the thermodynamic temperature of the triple point of water. Okay, so we say 1 Kelvin is defined as a fraction of 1 over 273.16 of the thermodynamic temperature of water. So you could imagine to say you had a temperature scale, then you chopped that temperature scale into that many equal parts. So each and every part of that temperature scale would give you what you consider to be 1 Kelvin. Is this clear? Yes?
The triple point of what?
Is there a what? One person at a time?
I would like to know what you said about the triple point of water.
The triple point is a condition where a substance exists as a solid, a liquid, and a gas at the same time. That's what the triple point is.
Okay.
At the triple point of something, of a particular substance, that particular substance will exist as a solid, as a liquid, and as a gas at the same time. In the case of the triple point of water, the temperature is 273.1615 kelvins. That's the thermodynamic temperature of the triple point of water. So we define 1 Kelvin in terms of this thermodynamic temperature of the triple point of water as a fraction of 1 over 273.16 of the thermodynamic temperature of the triple point of water. Are we clear? Again, these are definitions.
Not really, sir. So you mean it was to get like a sample of water, and then
Sorry?
you want to introduce the same conditions that you said to that particular sample of water. It will exist. Will it exist at a triple point?
What?
Then if you were to get like a sample of water,
Yes.
and then you were to
Yeah, if you were to get a sample of water,
introduce the same,
yes.
and then you were to introduce the conditions that you have stated,
Yes.
it will exist at the triple point.
Yes.
Okay, thank you.
Yeah. So if you get water in a glass, then you reduce the temperature of the water to this, then also you pump out air so that only this much pressure remains. Then you should be able to see something like this, where the water exists as a solid, as a liquid, and a gas. That's what we refer to as a triple point of water. Okay, so for you, the important bit to notice is that when we talk about temperature, we are talking about, in physics, when we talk about temperature, we are actually talking about a temperature called thermodynamic temperature. Okay, and this thermodynamic temperature actually measures the total energy of all the atoms which make up a solid. Okay, so what you feel as hotness, when you touch something, then you feel that it's hot. It's because the atoms or whatever it is, molecules of that particular substance have got a lot of energy. If you touch something, it feels cold. It is actually because the atoms or the molecules which make up that particular thing do not have a lot of this internal energy. Okay? So, in a nutshell, coldness and hotness is not a good measure of temperature. Okay? Because first of all, it's quite dangerous because you have to touch things. But when you measure temperature in terms of their energies, then that energy transferred onto a scale, in this case, which is the scale you're transferring the energy to is what's known as thermodynamic temperature. Then you can have on a scale and you see a number. Sorry? Some people should turn off their mics. Okay. So that's what temperature is. The total energy of an object measured on a scale. And in our case, in physics, this temperature is thermodynamic temperature measured in kelvins. There is a connection between the Kelvin and the degree Celsius, as we're going to see later on during the week. Then the next thing is electric current. Electric current refers to how fast something called electric charge flows through a point or a region. So the rate of flow of electric charge or current. Now, electric charge, for you to have electric current, you need electric charge. And this electric charge is found in certain particles like electrons and also protons. However, protons, like as you can see in this diagram, protons live at the center of the nucleus. So the nucleus, they don't really move to anywhere. The only other particles which have got electric charge which can move are electrons. However, again, there's a bit of a problem because not all electrons take part in electric current. It's only a few electrons which have been lost from an atom. These electrons which have been lost from an atom are the ones which take part in conducting this electric current business. So when an atom loses an electron into whatever substance it is, this atom is found. So when an atom loses an electron, then this electron becomes a street kid electron, like that, in quotation marks. That electron is able to move around inside that particular substance in a random way. Okay. The other thing, apart from having mass, which an electron has, is something called electric charge. I think you are aware that electrons are negatively charged particles. Okay, so electrons have got another physical quantity called electric charge, and they carry a very, very small amount of this electric charge, negative charge, which is, I think, minus 1.8 or something, 1.6, but it's very, very small, times 10 to the power minus 18 or 19 coulombs. So they carry a very small amount of electric charge. So as these electrons are passing through a point, you can imagine an electron carrying a small amount of charge in its pocket. As they pass through a point, you can actually, by counting how many electrons are passing through a point, you can actually in turn count how much charge is passing through that point. So electric current is defined in terms of the charge which has passed through a point, which charge is carried by electrons. Are we clear?
Yes, sir.
Electrons which have been lost from an atom, for example, this electron here, if this electron is lost from an atom, it becomes a street kid electron, or what we call a conducting electron, or a free electron. Are we clear on this one? That atoms can lose electrons.
Yes, sir.
Atoms can lose electrons, atoms can gain electrons, atoms can share electrons with other atoms. Our interest is in atoms which lose electrons. And these atoms which lose electrons, Catherine, can you switch off your microphone? The atoms which tend to lose electrons are mostly found in metals. Okay? Atoms found in metals tend to lose electrons. So these electrons, when they are lost, they no longer belong to that particular atom, but they just move around the metal, move around the metal in a random way. Okay? So if a piece of metal has got billions of atoms, then each of these atoms in the metal loses one electron. So what you end up with is billions of street kid electrons, or free electrons, or conducting electrons. Okay? Each of these electrons carries a very small amount of electric charge. So when they pass through a point, these electrons, as they pass through, they are actually carrying this electric charge. So you can measure how much electric charge is being carried by the electrons, since each electron carries a fixed amount of electric charge, a very small but fixed amount of electric charge. So by measuring how many electrons have passed through a point, you can actually calculate, say, this is how much electric charge has passed through a point in 1 second. That's what is referred to as electric current. Is that clear? Here is a picture trying to show the flow of electric current.
Yes.
Okay. Are we clear on this?
No.
Where are you not clear? Where are you not clear?
Clear.
Okay. The electric current is measured in amperes.
We are clear.
Okay, so the electric current is measured in amperes.
Sorry, sir. Excuse me.
Yes.
What you said about measuring the current, electric current.
What about it?
Yes, said to, yes, it said you can measure electrons concerning about how it has passed a point.
You can
That's
count
why-
how many electrons are passing a point. Because each electron carries a small amount of electric charge. So from the number of electrons passing through a point, you multiply the number
Does
of...
not determine the current flowing on it.
Sorry? From the number of electrons passing through a point, and each electron is carrying a small amount of charge, you can find out how much electric charge has actually passed through a point. Are we clear? Yes. So, how much electric charge has passed through a point divided by how much time it took for the charge to pass through that particular point, that is what is known as current. Okay? If so much amount of charge passes through this particular point in 1 minute, then you divide that size of charge by 60 seconds, because 1 minute has got 60 seconds. So you find out how much charge is actually passing through a point in 1 second. That's what current is. It is how fast charge is flowing through a point. Each electron carries a small amount of electric charge, about 1.6 or 1.8, or I think 1.6 times 10 to the power minus 19 coulomb of charge. So if each one is carrying this amount of charge, then billions of them pass. So you multiply billions, their number, times the charge, then you find out how much charge has passed, then you divide by how much time it has taken. Okay. So
Excuse, sir.
yes.
I can't see your screen.
Okay, so electric current is measured in amperes. Okay. Currently, the definition of an ampere is in terms of, it used to be defined like this. So you would get, this whole thing had to be done in a vacuum. So already you can imagine this must have been difficult to do. So in a vacuum, you would get a 1 meter conductor, another 1 meter conductor, then you would put them at a distance of 1 meter, then you pass a current through them. Okay. Then when current is passing through a conductor, that conductor basically becomes a magnet, but a very weak magnet. Like in the case of an electromagnet is just a wire, then with windings, then you pass current through it, then it attracts things. Okay, so the same thing applies here. When current flows through a wire, that wire actually acts as a very weak magnet. So this setup of defining an ampere had its own problems. One, you needed a vacuum. Two, you needed a way to measure how much the force of attraction was between the wires. If the force of attraction was 2 times 10 to the power minus 17 newtons, which is a very, very, very small amount of force, then you would say that the current flowing through the conductors was 1 ampere. So apart from having a vacuum, the long wires placed 1 meter apart, you also needed a way of accurately measuring the current, measuring the force of attraction between the wires. So this was very difficult to do. Yes, it served as a definition, but practically it was difficult to do. However, what was easy was to use, as of 2019, what was easy to do was to actually use Holm's law. So Holm's law basically gives you the relationship between the voltage, the current, and the resistance in a conductor. Between the points of a conductor, what's the voltage, how much current is passing through, and what's the resistance of the conductor. And that relationship is this. Voltage is equals to the electric current multiplied by the resistance. Okay? So if you make the current the subject of the formula, then you measure the voltage and the resistance, then you could find the current. So you could find how much current is actually passing through a wire by just measuring the voltage and also the resistance. So if the voltage you measured was 1 volt, and the resistance of the conductor was 1 ohm, then we would say that the current passing through the wire is 1 amp. So this is a much more practical way of defining the ampere, 1 volt per ohm. Okay, so you get a voltmeter, you measure what the voltage. Okay, then you work out what the resistance is. Maybe you're just using a normal resistor, then you know from the color codes whatever the resistance is. Then if the voltage is 1 volt, then the ohm is 1 ohm, whatever it is, or 10 volts divided by 10 ohms, you still get 1 amp. Are we clear?
Yes, we are clear.
Okay, need to admit someone. Okay, the next physical quantity is something called amount of substance. Now, amount of substance is related to the mass, but it's not the same thing as a mass. Okay, because amount of substance is concerned with how many atoms, molecules, or electrons are actually in a substance. Amount of substance is measured in moles. And how do we define a mole? Well, 1 mole of a substance contains the same number of atoms as they are in 12 grams of carbon-12. So you have to have a mass of this thing called carbon-12. Now, carbon-12 is charcoal. Malasha. If you go to the market, there's load shedding, then you go and buy malasha. That malasha you're buying, that's what's referred to as carbon-12. Okay? So if you go to the market, then you buy this malasha, carbon-12, then you pound it so that you have a powder. Okay? Then you weigh out, you measure 12 grams of that charcoal. If it's exactly 12 grams, that 12 grams you have of charcoal, that's what's referred to as 1 mole. Okay? And the special thing about that 12 grams you're going to measure out is that it contains this many atoms. 6.0221486 times 10 to the power 23 atoms. So in that 12 grams, there are 6.0221486 times 10 to the power 23 atoms. That's what's referred to as 1 mole. So, as an extension of this definition of the mole, any amount of a substance which contains this number of atoms, that is referred to as 1 mole. 1 mole of any substance contains 6.0221486 times 10 to the power 23 atoms, or molecules, or ions, or electrons. Are we clear on what a mole is?
Yes.
Okay. The other thing you're supposed to be aware of is that atoms of different elements have got different masses. Are you clear? Are you aware of that? An atom of copper, an atom of carbon, an atom of aluminium, they don't weigh the same. They've got different masses. So the thing is, if we are counting the same number of atoms, but these atoms have got different masses, it means that for each mole of any substance, we will need to weigh out different amounts, different masses. And that mass of a particular substance you weigh out, which gives you this number of atoms which make up 1 mole. That is what's known as the molar mass. Okay? For example, in the case of zinc, here, as you can see from the diagram here, you need 65.4 grams of zinc. If you've got 65.4 grams of zinc, then you say you've got 1 mole of zinc, because the number of atoms in that 65.4 grams of zinc is this. If you have 12 grams of carbon, then we say you've got 1 mole of carbon because the number of atoms is this. Magnesium, you need to weigh 24.3 grams of magnesium for you to have 1 mole of magnesium, because the number of atoms in this amount of magnesium is this. Copper, you need to weigh 63.5 grams of copper for you to have 1 mole. Again, you'll notice one thing here. Mass and the number of moles does not care about the shape of the substance. It only cares about how many atoms are there. Here you've got a powder, here you've got some grains, here the copper wire, you've got wire, okay? Then here you've got another powder for sulfur, then for silicon, then for lead, then for tin you've got something which looks like stones or something like that. The amount of substance does not care about the shape or about the volume. It only cares about how many atoms are actually there. If the number of atoms is this, 6.02214,086 times 10 to the power 23, then you say you've got 1 mole of a particular substance. This number is what's referred to as Avogadro's constant. Are we clear?
Yes. No, I'm not clear.
Where are you not clear?
I'm not clear. Can you explain more on the Avogadro's constant?
Avogadro's constant is this number. This number. The number of atoms you need for you to have 1 mole of a substance. That number, that's Avogadro's constant, Avogadro's number. That's what you're going to use in chemistry to find out how many moles of a particular substance you have. Are we clear?
I have a question, sir. Yes.
Yes. What's the question? Yes.
So, 1 mole does it mean that 1 mole of any substance equals to Avogadro's constant?
No. 1 mole of any substance has the same number of atoms as Avogadro's constant. 6.02214,086 times 10 to the power 23 atoms or molecules. It's not equal to Avogadro's constant. It has got the same number of atoms or molecules as Avogadro's thing.
Okay.
Yes.
Okay, thank you.
Any other questions?
Excuse me.
Yes.
About the amount of the substance, you said the amount of the substance doesn't care about the mass.
No, I didn't say it doesn't care about the mass. It says it doesn't care about the shape.
Okay.
Because here you've got a powder, here you've got a wire, here you've got something which looks like stones, here you've got stones, a powder, grains, stuff like that. So you've got all sorts of different shapes of substances, but they have got the same number of atoms. They are all 1 mole. Each of these things you're seeing there is 1 mole, 1 mole, 1 mole, 1 mole. Of course, the more mass you have, the more atoms you're going to have, which means the number of moles is going to increase. The number of moles is equal to the mass of a particular substance divided by the molar mass. So it is related to the mass in a certain way. How many moles you have is related to how much mass you have. So you divide the mass by the molar masses for you to get the number of moles. Any other question before we move on? Okay, so I'll move on to something called light intensity. So, light intensity, I'll first start with the definition. Then I'll break down the definition in small bits so that we understand. Light intensity refers to the luminosity per solid angle. That's what light intensity is. So the next question is, what is luminosity? What is solid angle? Because what you're actually doing with light intensity is here. Light intensity, You get the luminosity, then you divide the luminosity by the solid angle, then you get light intensity. So what is it? What do these things mean? Well, luminosity, this luminosity in physics refers to something luminous is something which emits light. Okay? So luminosity is a measure of how much light is being emitted, not just any light, the amount of visible light, the light you can see, how much visible light is being emitted by a source of light in all directions per second. That's what luminosity is. How much visible light is being emitted by a source of light in all directions per second. This luminosity is what you see when you go and buy a light bulb. It says 6 watts, it says 9 watts, it's saying 15 watts, or it says 20 watts. That watt thing there is telling you how bright the light is going to come out of this source of light, the bulb you have bought. So if it says 6 watts or it says 9 watts, it means that in 1 second, this bulb is going to emit 6 joules of energy or 6 joules of visible light in all directions per second. That's what it means. That's what luminosity is. So luminosity is connected with the source of light. How bright is it? Are we clear?
Yes, sir.
That's luminosity. Okay. Now, the other thing I want you to take note of is that the light from the bulb has to go somewhere. Okay? The light from the bulb has to fall somewhere. It needs to fall somewhere. Okay? So the area, look at this diagram. If you imagine at the center of this diagram here, there is a source of light, a torch. Then that light shines on this area, this orange area here. Okay? This is an area which is being shone on by the light from the torch. Okay, on a wall. So that the light from the torch covers this much area. Okay? Then this area on which the light has fallen is located at a distance r from the source of light. So the area on which the light has fallen divided by the distance squared. So here, the area on which the light has fallen, the light from the source of light on which it has fallen, divided by the distance squared. The distance from the source of light squared. That's what gives you solid angle. So the solid angle has to do with where the light has fallen, then divided by the distance from the source of light, but the distance is squared. Is that clear? On what solid angle is? Yeah, okay, fine.
No.
Huh? Someone said no. Where is the problem?
Yes, I didn't get it. So if you could kindly go through it again.
Which part did you not get? Is it the luminosity or the solid angle part?
The solid angle part.
Okay, so imagine, have you ever seen a torch?
Yes.
Do you have one in your house?
Of course I have.
Okay, so if you switch on your torch, when there's load shedding, okay, you switch on your torch. So your torch produces light, okay? Now, if you move with your torch closer to the wall, okay, there is an area on which the light is going to fall, right? The light from your torch is not going to go everywhere. There's going to be a space on your wall where the light is going to fall. That area, you calculate how much area the light has fallen on, divided by the distance from the wall to where the torch is. But the distance is squared. That's what gives you the solid angle. It is a special 3D angle. It's a special angle. So if you move closer to the wall, if you move closer to the wall, the area on which the light is falling is going to reduce. If you move the torch away from the wall, the area increases.
Okay, sir.
Yes. So that area divided by the distance squared, that's the solid angle. So in a nutshell, when we are talking about light intensity, basically what we mean is, if you have a smartphone, okay, then you switch on your flashlight. Then after you switch on your flashlight, you put your flashlight on your skin. After a few seconds of doing that, you are going to feel that actually light is burning your skin. The light is burning your skin. Sorry? Why did we square the distance? Because we are looking for an angle. We need to divide the area. The area is measured in meters squared. Okay? So the distance has to be squared so that we cancel out the meters, so that we end up with an angle. So when you switch on your flashlight for your phone, then you put your flashlight on your skin. In less than 30 seconds, I think, or less than 1 minute, you're going to feel a burning sensation on your skin. That burning sensation from the light, that is what we call light intensity. It is a combination of the luminosity from the source of light, the area on which the light is falling, and the distance from the source of light. If you start moving your flashlight away from your skin, the amount of burning you're going to feel is going to reduce. So the light intensity reduces. So the more if you move the source of light closer to your skin, the light intensity increases. If you move it away, the light intensity reduces. So this burning sensation you're going to feel when you're closer to a source of light, that's what is called light intensity. Are we clear? Okay, so this, yes. So this light intensity, when you divide an area which is in meters squared divided by a radius in meters squared, what you get is solid angle, and the units of solid angle are what are known as steradians. Okay, SR, steradians SR. So, and this is the formula for solid angle. Omega is equal to area divided by radius squared. So steradians, so luminosity is measured in watts, then steradian, solid angle is measured in steradians. You divide these, then you get yourself what is known as a candela, which is the unit for light intensity, or standard candle. 1 watt per steradian. How can we make sense of this? 1 candela is defined as 1 watt per steradian. So you do the following. You get a bulb, okay? You get a bulb which has got the wattage of 1 watt. So you put a 1 watt bulb at the center of this thing here, of this circle. Then this bulb is going to shine some light here. The area, if the area of this thing is equal to the radius squared, if the area is equal to the radius squared, then what you have is something called 1 steradian. So 1 steradian divided by 1 watt, then you get yourself 1 candle, or 1 candle. Are we clear? Do we have any questions? So the point really of this lesson is we all come to the same page. Okay? When you talk about mass, what is it you're talking about? When you talk about length, what is it you're talking about? When you talk about time, what do we mean by time? we don't mean when you have breakfast. No. What you mean is how long is your breakfast. That's when you talk about time. When you talk about temperature, what do we mean? When you talk about electric current, what are we talking about? When you talk about amount of substance, what do we mean? When you talk about light intensity, we need to be on the same page, because these 7 quantities are the basis for obtaining all other physical quantities. The other physical quantities which are not these 7 are what are known as derived quantities, and these are what we're going to look at next time we meet. When is that? When are we meeting next? I'll find out anyway. So the next time we're going to meet, we're going to look at something. Thursday?
Thursday, yes.
Yes, so the next time we're going to meet,
Yes,
we're going to look at how to obtain derived quantities from these base quantities. The thing to note about derived quantities is you obtain them by doing a multiplication or by doing a division, or by doing both multiplication and division. Then you obtain your derived quantities. So we're going to see how to obtain different physical quantities by doing multiplication and division. So that's what we're going to discuss. So that must be much, much easier since you've got the notes. Okay, so we come to an end here. Unless you've got questions, please ask now, otherwise we have to stop.
I have a question, sir.
Yes, Sylvester.
As TG73 is clashing with the lecture on Thursday, so...
I am not in charge of TGs. So you have to speak to the assistant registrar or the
Sir,
head of
I've got a
department.
suggestion. I was thinking next time when we meet, why can we use Zoom?
Why can't you use Zoom? I'm not familiar with Zoom. What's wrong with this one?
Yes, sir, the next time.
What's wrong with this?
This one is tripping. Like, really, it's tripping, sir, it's tripping.
Okay, so you can...
And at some point you are cutting.
But I'm sure Zoom also does the same thing. It's just the internet. Okay, those points where it was cutting, there is a recorded video which we have made. So we're going to upload the recorded video of the same thing to the Moodle and also YouTube. So the recording is going to be there, so you can still watch it. The thing which hasn't tripped or whatever it is you're calling it. Are we clear?
Okay, thank you, sir.
Yes, sir.
Sir,
Yes. Next question.
the question is on the area of finding the
The area of what?
The question is on finding the area for that luminosity.
Solid angle.
Are we squaring also the rate?
Are we what?
Are we also squaring the radius? when we're
No,
finding
actually that
the area
radius
for,
is the
the
distance.
luminosity?
It's a radius of this circle. If you look carefully the way things have been, it's a radius of this circle, which is the distance from the source of light, because the source of light is the center here. So this radius is actually the distance from the source of light to where the light is falling. Have you seen that? So it's not the radius of this shiny thing. No, it's a distance. It's a radius of this circle, this ball. Okay? This radius of this ball. The radius of the ball
Sure.
is the distance from the source of light at the center to where the light is falling. So in other words, this R is the distance from your source of light to where the light is falling. So we square that. It's not the radius of the thing. Whatever, your source of light can be anything. It can be a circle. Your torch can have a circular thing. It can be a square. It can be anything. So it's just the area divided by the distance from the source of light to where the light is falling. But the distance is squared.
Alright.
Okay. All right. Let's come to an end. Unless there is another question. So if there are no questions, let's come to the end. I will leave the video to upload to YouTube, then I'll add the link to the YouTube on your Moodle so that those people who haven't watched or who are not listening clearly or there was problem with the network,
Sir,
you can watch again. Yes.
are we going to be having in physics on Monday and Fridays?
Yes. For the rest of the year, you're going to be having physics only on Monday and the other day. I don't know whether it's Friday or whatever day it is. Ati?
As a group, or only on Mondays and Fridays?
Is it Monday and Friday or Monday and Thursday? I don't know. Which one is
Are we
it?
all going to be having on Mondays and Fridays?
Group O.
Monday and Thursday.
Monday and Thursday. Thursday morning. So Thursday at 8 hours to 9 hours. So
Monday and Thursday.
yes. Monday and Thursday, you're going to be having lectures for the rest of the year.
On the same link. Just
And when are we likely to expect the first tutorial sheet?
When are you expecting the first? People are still working on that. Somebody is working on the tutorial sheet stuff.
And then the books which are recommended on Moodle, those are the books we're supposed to be studying in case we want to like study ahead.
Yeah, you can study. Those books which have been put on Moodle are there to show you how the physics you are learning is used in medicine. Okay? So they show you how the physics you are learning is going to be used in medicine. So even as you try to become a medical doctor, don't think that physics has got no applications in the human being or in medicine. Okay? So when you read those books, you see examples of where the physics is actually used in medicine. So the first thing we have to do is we need to teach you the physics. That's the first thing we need to do. We need to teach you the physics. Then when you read,
So like when the tutorial sheet comes out.
yeah, when the tutorial sheet comes out, your tutorial sheets should have problems which will need to be worked out. Again, since you'll be most likely be at home, those problems have to be worked out online. There's a way we do this thing. So yeah, don't worry so much about how the tutorial is going to be done. For myself, I'm also going to be organizing, like I said, tutorials 2 days in a week for you guys, another 2 days in a week for the guys who are studying PHY 1010. Again, those tutorials are going to be recorded so that you can watch them if there was load shedding or you're not able to log on. Okay, but that should be probably in the next month or something like that for us to start tutorials, because you need to cover some material for you to do tutorials. All right, let's come to the end.
Sure.
Yeah, data is going to finish. Okay, I'll stop sharing and I'll stop the recording.